So today we're looking at rational functions and discontinuities and end behavior. So here are examples of rational functions. It's a function whose rule is the quotient of two polynomials. Let's go ahead and talk about continuous graphs. Continuous graph is a graph with an unbroken curve. There are no jumps, no breaks, no holes in the graph. So it says, is the graph below continuous or discontinuous y? So if we look at number 1, right away we can look at the graph and say we know it's discontinuous because we see that there are breaks in the graph here at -2 and 2. So the question is, how do we algebraically look at this function and decide or determine that that's going to happen? So remember we said we can't divide by 0, and I have a variable in my denominator which could possibly make it 0. So the first thing I would do is go ahead and factor this. So if I factor, this is a difference of 2 squares, so that becomes x plus 2 times x minus 2. And remember yesterday we talked about the fact that the zeros of the denominator are going to give us our vertical asymptotes. So if I set each of these factors equal to 0 and solve, I get x equals -2 and x equals 2. That actually gives me my vertical asymptote on my graph. So of course this is discontinuous. And the discontinuities, we would say, are vertical asymptotes at x equals plus or minus 2. Looking at question number 2, we can again see right here we have another vertical asymptote. So this means that this is going to be a discontinuous graph. So what are the discontinuities and how do we find them? Again, we're only concerned with variables that can make the denominator 0. So I take this, set it equal to 0 and solve, and I get x equals -1. So this is again discontinuous at a vertical asymptote at x equals -1. Yes, it's important that you specify whether or not it's vertical asymptote or whole, or we'll also talk about horizontal asymptote, so it's important to write it out. Looking at number 3, this does not appear to have any discontinuities, but sometimes it's hard to tell because we have what we call holes in the graph, which we'll talk about in a little bit. Not just the vertical asymptotes, but also holes. So looking here, remember again, we want to take what's in our denominator and set it equal to 0 because we can't divide by 0. So if I solve this, I get x squared equals -1. So now I want to get rid of that power 2 by taking the square root of both sides. So this would be plus or minus the square root of -1. Remember, if we have a negative underneath the radical, that becomes I. So this is actually plus or minus I. So that means that no matter what I plug in for this variable, nothing is going to make my function get 0. Because if I plug in 0 and square it, I'm still adding 1. If I plug in a negative number and square it, I'm still adding that 1. So that means that this denominator will never equal 0. So the graph is continuous. Okay, so let's go ahead and move down to asymptotes. We've talked about asymptotes before. They're the line the graph approaches but does not cross or touch over. And so we're going to talk about 3 different kinds of asymptotes in this section. We're going to talk about vertical asymptotes. We are going to talk about horizontal asymptotes and slant asymptotes. The horizontal and slant asymptotes are actually what we call the end behavior of the graph for very large values of x. So what happens in the long run as your x values get large in the positive and the negative direction, what's happening to the ends of your graph. And we talked about end behavior when we talked about our polynomials. So discontinuities. Discontinuities happen when we have vertical asymptotes and also when we have holes. But we're going to go ahead and look at the vertical asymptotes first. So vertical asymptotes are called also non-removable discontinuity because, again, we can never divide by zero. And if you have a vertical asymptote, it's what happens when you get zero in the denominator. So these occur when there is something that x cannot be because it would make the denominator equal to zero, and we can't get rid of the factor from the denominator. So steps to find the discontinuity: factor and simplify, and then find the real values of x that make the denominator equal to zero. So for each rational function, find any points of discontinuity. So in order to do that, we want to factor. So if I go ahead and factor this equation, I have 1 over x plus 1 times x plus 1, because factors of 1 that add up to 2, because we have a trinomial right here. So then we set each factor equal to 0, and they're the same, so we don't really need to set them both equal to 0. You can just set 1 equal to 0 and solve. And so we get x equals -1. So if I plug -1 in for x, that means I would get 1 over 0. And so f of -1, 1 over 0, we can't have, right? That's undefined. So that means we have a vertical asymptote at x equals -1. So then for the next one, we're going to do the same thing. So let's go ahead and factor. So if I factor my denominator, because that's what I'm looking at right now, this factors into x minus 3 times x minus 2. We want factors of 6 that add up to -5. So then we're going to set each factor equal to 0 and solve. And when I solve, I get 3 equals x, and here I add the 2, and I get 2 equals x. So again, that means we have vertical asymptotes at x equals 3 and x equals 2. And yes, it is important to write x equals when you're writing out a vertical asymptote. Looking at the next one, same thing. If I go ahead and factor this factors into the difference of 2 squares. So x plus 4 times x minus 4, and then I'm going to set it equal to 0 and solve. So set each factor equal to 0, and I get x equals -4 and x equals 4. So that means we have vertical asymptotes at x equals plus or minus 4. And over here, if I solve, x squared plus 1 equals 0. X squared plus 1 does not factor, because remember, we don't have the sum of two squares, we only have the difference of two squares. So since this doesn't factor, if I go ahead and solve, x squared is equal to -1, and then x is equal to, when we take the square root away, when we take the square away, we take the square root of both sides, what I meant to say. So plus or minus square root of -1. So that gives us x equals plus or minus I. And we talked about this on the front. We said that this means that no matter what I plug in here, I can't get 0. So that means there are no vertical asymptotes. Not always are you going to have a point of discontinuity. So that's just what I'm showing you there. So the other discontinuity that we can have is called a hole. Now this is where it starts to get a little bit tricky. So a hole is called a removable point of discontinuity. And it occurs when there's something that x cannot be because it would make the denominator equal to 0, but we can cancel out the factor from the denominator completely. That's important. So steps to find the discontinuity: factor and simplify. Find the real values of x that make the denominator 0. Substitute x into the new equation to get the value, the y value, and then means you have a hole at x, y. So we're going to talk about holes, and then we'll talk about how to tell the difference between a vertical asymptote and a hole. So for this one, first thing you would do is factor. It's already factored. So if that factor that you have, so if I solve this, I'm looking for what makes the denominator 0, right? So if I take x minus 2, set it equal to 0, because we can't divide by 0, I get x is equal to 2. So I know this is my area of concern. So if I go ahead and plug 2 into this equation, 2 minus 2 is 0. So I would get, so if I do f of 2, I get 2 minus 2, and then x, oops, sorry, that'd be 2 minus 1 over 2 minus 2. So again, if you notice right there, this would be 0 times 1, so that's just 0 over 2 minus 2 is 0. So we can't have that. So that's how we know this is an area concern. So in the problem, this is different than a vertical asymptote because notice you have a common factor in the numerator. So if I have a common factor and that factor cancels completely out of my denominator, I can rewrite my new equation. So the new equation would be f of x equals x minus 1. So remember, when you simplify something, that means that it is the same thing. You know, you're just setting equal to what it is originally equal to. It's just kind of changing what the equation looks like. So we're just getting rid of that x minus 2. So when I simplify it, notice that there's nothing in the denominator anymore. So the reason I know that this is going to be a whole, because now if I plug 2 into my simplified version, I get 2 minus 1. So 2 minus 1 is 1. So that means that f of 2 equals 1. So this is a whole at 2 comma 1. And so that means that if I were to graph this original equation and this equation, the graphs would look similar. But because the original equation has something that makes our denominator 0, there's actually going to be a hole in the graph. So let's go ahead and actually plug those in to our y equals on our calculator, just so you can see what it is we're talking about. So for this, make sure you use parentheses, and I would do double parentheses because you have two binomials in the numerator. So x minus 2 times x minus 1, close that parenthesis twice, divided by, and then parentheses, x minus 2. And if I go ahead and hit graph, I'm going to go ahead and zoom 6, which is a standard window. So if I look at this graph, notice that it looks like a straight line. And if I go to my table, second graph, notice there's an error at 2. If I go back to my graph, if I hit second trace value and x value 2, notice there would not be anything there because there's a hole in my graph, because the original equation, then if I look at it, it has something that a value of x that could possibly make our denominator 0, which is 2. So if I look at just x minus 1, now this graph is going to look like the graph we just did. So you have just graphs it on top. The simplified graph we like because the simplified graph, if I look at the table, it will tell you where that hole would be if the hole wasn't there. So by canceling it out from your denominator, you're saying, okay, well, if that hole wasn't there, it would be at 2 comma 1. So that's how you find the holes of your graph, by using that simplified version. So let's go ahead and look at the next one. So if I look at this problem here, again, the first thing I want to do is factor. So you want to factor both the numerator and denominator. So the numerator is the difference of two squares. So x plus 1 times x minus 1 over x plus 1. And then I would notice that the x plus 1s cancel out because it's common factor between the numerator and the denominator. So when I simplify, I get x minus 1. So going back to the original problem, that's going to tell me my restriction. So x plus 1 equals 0, so x equals negative 1. So I'm trying to figure out, is that vertical asymptote or whole? And so the reason I know it's a whole is because when I put it into my simplified answer, f of negative 1, I get negative 1 minus 1. So f of negative 1 is equal to negative 2. Because it gives me a value and not some error, I know this is a whole at negative 1, negative 2. If instead it gives me an error because you have 1 over 0 or some number over 0, you know that it's going to be a vertical asymptote. So we're going to do some examples of that. So as you've noticed, some functions may have more than one type of discontinuity in them. How do we determine if it's a vertical asymptote or a whole? So if it crosses out the denominator completely, it is a whole. If it doesn't cross out of the denominator completely, then it's going to be a vertical denominator. or basically when you plug the number in that makes your denominator 0 from the original equation to your simplified answer, if it still makes the denominator 0, again, it's a vertical asymptote. So let's do some practice. So for each rational function, we're going to describe any discontinuities. So we want to figure out, is it a whole versus a vertical asymptote? So which one is it? So looking at this first one, first thing you want to do is factor the numerator and denominator, which is already done for us, which makes it easy. So then we're going to take whatever is in our denominator from our original problem, set it equal to 0 to figure out what makes our denominator 0, because we can't have those values. So if I solve this, I get x equals 2, and here I get x equals 3. Well, notice that nothing cancels out of here. So since nothing cancels out, I'm going to plug these numbers in. So if I plug these values in, f of 2, I get 2 plus 1 over 2 minus 2 times 2 minus 3. So that gives me 2 plus 1 is 3 over 2 minus 2 is 0, and 2 minus 3 is negative 1. So that gives me 3 over 0. Well, because I have 0 in my denominator, when I plug that in, that's how I know it's a vertical asymptote. So vertical asymptote at x equals 2. If it was a whole, I would actually get a value other than 0 in the denominator. So f of 3, if I plug it in, I would get 3 plus 1 over 3 minus 2 and 3 minus 3. So that gives me 4 over 1 times 0, which is 4 over 0. So again, undefined. So that means x equals 3 is also a vertical asymptote. Looking at question B. So for question B, again, the first thing you want to do is factor. The numerator doesn't factor any further, and the denominator is the difference of two squares, so x plus 2 times x minus 2. And notice that we have a common factor that we can cancel. The x plus 2 cancels out of the numerator and denominator, and so since it cancels out, I can rewrite this equation. So if it's gone completely from the numerator and there's nothing in there, it's just 1 over x minus 2. So that is the simplified answer. So now we're going to use this to check our values. So if I go back to the original problem, I need to set those equal to 0, so those numbers of x, because remember, always look at your original problem to figure out what values you can't have in the denominator, so negative 2 and 2. So now I'm going to use this simplified answer to check these values. Always use your simplified, because if I get a number, then I know it's a whole. If not, then I know it's a vertical asymptote. So if I plug in negative 2 here, I get 1 over negative 2 minus 2, which gives me negative 1/4. Since I got a number that tells me this is a whole, so I have a whole at the x value I plugged in was negative 2, and the y value I got out was negative 1/4. So I know that's a whole. Now I have to check the other value, which the other value that I have is at x equals 2. So if I plug in 2 into my simplified answer, f of 2 equals 1 over 2 minus 2, which gives me 1 over 0. So again, that is undefined. So that means that at x equals 2, it can't be a whole because I didn't get a value in my simplified answer. So that means that it's a vertical asymptote at x equals, in this case, we plugged in 2. So we have a vertical asymptote and a whole. Now, a whole can't also be a vertical asymptote. You can only have one or the other, but you can have a whole and you can have a vertical asymptote in your equation like we have right here. So let's go ahead and take a look at the graph of this. So if I plug this into my graphing calculator, and of course when we are doing these, just use your graphing calculator to check, because we need to know how to do these without using our calculator. So we have parentheses x plus 2 divided by, and then in our denominator we have x squared minus 4. And if I look at the graph, you'll be able to see There's a vertical asymptote right here at x equals 2, but notice there isn't another break in the graph that we can see. So if I do second trace value, -2 was the other value that we're looking at. Notice that nothing comes up. So since you don't see a break like this where it branches off, that's how I know there's a hole in my graph. So I can also confirm by looking at the table, I should have 2 errors, one at 2 and one at -2, which I do. So again, just to clarify, when you are trying to find the values that make your denominator 0, always use the original one. When you're checking if it's a vertical asymptote or a hole, use the simplified one. If when you plug it in, you get a value that doesn't have 0 in the denominator, then that's a hole. If it gives you 0 in the denominator, when you plug it into the simplified answer still, then it's a vertical asymptote. So let's go ahead and take a look at the next question. So for the next one, the first thing we need to do is factor. So this factors into, we want factors of 12 that add up to -7, so x minus 4 times x minus 3. And in my denominator, factors of 9 that add up to -6 would be x minus 3 times x minus 3. And this doesn't factor any further, so x minus 4. And then I'm going to simplify. So the x minus 3's, these cancel out. The x minus 4 cancels out with this x minus 4. So when I simplify, I get everything canceled on my numerator, so just 1 over and then x minus 3. But remember, when we're looking at our discontinuities, I want to use the original problem, what makes that denominator 0. So this would be, of course, what would make this 0 if x was equal to 3. Same thing here, and here what would make this 0 if x is equal to 4. So these are the two values that I'm going to test in my simplified answer. I don't want to test them in my original one because I know they would give me 0 over 0, or it would give me, 0 over 0. So f of 3, in my simplified answer, I get 1 over 3 minus 3, which is 1 over 0, which is undefined. So that tells me that we have a vertical asymptote at x equals 3. So now let's go ahead and test the other value. If I do f of 4 in my simplified answer, I get 1 over 4 minus 3, which gives me 1 over 1, which is just equal to 1. Because it gives me a y value, that tells me that is a hole. So we have a hole at 4, comma 1. So why don't you go ahead and pause the video and do example D and E on your own. When you're done, you can unpause to check your work. All right, looking at D, if I factor this, nothing factors. So we're going to go ahead and take the denominator values, set them equal to 0 to find what my areas of concern are. So x equals 1 and x equals -3. Now this does not simplify at all. So if I plug these into the equation that simplifies, if it doesn't simplify, you plug it into the original equation, I know they're going to make my denominator 0, so I know these are both vertical asymptotes. But if you still need to plug it in, that's fine. So if I plug the values in to my equation, I would get, if I plug in 1 into the numerator, 1 minus 2 would give me -1 over, and in my denominator, I would end up with 1 minus 1, which is 0, and 1 plus 3 is 4. So notice I get -1 over 0, which is undefined. So vertical asymptote. F of -3, if I plug that in, I get -3 minus 2. So -3 minus 2 gives me -5. And if I plug in -3 into the denominator, -3 minus 1 gives me -4, and -3 plus 3 is 0. So negative 5 over 0, again, we can't divide by 0, which is undefined. So again, that means we have vertical asymptotes at x equals 1 and negative 3. All right, looking at the next question, first thing you want to do is factor. The numerator doesn't factor any further. Denominator factors of negative 15 that add up to 2, so x minus 5 times x plus 3. So we use these two values to figure out what our discontinuities are going to be, where they're going to be at. So here I get x equals 5 and x equals negative 3. If I go back to my equation, it simplifies so that x plus 3 cancels out. And since it cancels out, I can go ahead and rewrite the equation as 1 over x minus 5. So I'm going to use this to help me determine if the value at 5 and negative 3 are vertical asymptote or whole. So let's go ahead and test f of 5 first into the simplified answer. So f of 5, when I plug it in, I get 1 over 5 minus 5, which is 1 over 0, which is undefined. So we can't have that, so we know that that is going to be a vertical asymptote at x equals 5. If I plug in negative 3, f of negative 3 gives me 1 over 3 minus 5, which is 1 over, sorry, that's negative 3. So negative 3 minus 5 gives me 1 over negative 8. So because I didn't get 0 in the denominator, that means that at negative 3 we have a whole. So there is a whole at, and you want to always write the coordinate pair, negative 3 comma negative 1/8. Because we will be graphing these without using our graphing calculator, and so you need to be able to mark specifically on the graph where the whole is, and so by plugging into the simplified answer, that's how you get where that whole is, so you know where to put it on the graph without using your calculator. Next, we're talking about horizontal asymptotes. So horizontal asymptotes describe the end behavior of the graph as the x values get large in both the positive and the negative direction. The graph of a rational function has at most one horizontal asymptote. We, when we're looking at these, we want to always look at these in standard form. So the equation must be in standard form. It's unlike finding vertical asymptotes and wholes, you want to use the factor form. But for horizontal asymptotes, you always want the equation to be in standard form in order to check. So the three cases. Case 1, when the numerator degree is less than denominator degree, then you're going to have a horizontal asymptote at y equals 0. So this is the numerator is less than the denominator. You'll see me write that out. When the numerator degree equals the denominator degree, then the asymptote is going to be y equals the ratio of the leading coefficients. And when the numerator degree is greater than the denominator degree, there is no horizontal asymptote. And instead, we have a slant asymptote. Or other asymptote, but we're not going to talk about other asymptotes besides slant. So to find a slant or oblique asymptote, you're going to divide the two polynomials, and the quotient of the polynomial is going to be the asymptote that describes the end behavior of the graph. So for example, find the horizontal or slant asymptotes. Looking at the first equation, again, it must be in standard form in order to determine this. So remember, this is in standard form. you're looking at the degree. So the degree of the numerator in standard form is the highest power of x, which this is of 1 if it's not written. So we have degree 1 over a degree of 1. So that means the numerator equals the denominator, and we're using case 2 for the end behavior. Case 2 says the horizontal asymptote is the ratio of the leading coefficients. So the leading coefficients, this is 1 if it's not written, are 3 over 1. So that means we have a horizontal asymptote at y equals 3. So if we look at the graph on our calculator, just to show you, again, horizontal asymptote is the end behavior. It's not the vertical asymptote. So we're not looking at right here. We're trying to figure out what's happening as we get very large values of x in the positive and the negative direction. So if I hit trace and maybe do the negative direction first, if I keep going to the left or towards negative infinity for x, notice that your y values are going to get closer and closer to 3, but they're not actually going to reach 3. But if I kept doing this, it would just get closer and closer each time. And so that is, again, what the end behavior is, what happens in the long run to the ends of our graph, which is why it's called end behavior. Looking at the next one, we have, again, standard form. We have degree 2 over, and this would be degree 2. So again, the numerator degree equals the denominator degree. So you look at the leading coefficients. So in this case, that means there's a horizontal asymptote at y equals 2/3. Here, if there is no x, remember that x to the 0 power is the same thing as 1, because anything to the 0 power is 1. So that means this is at degree 0 over degree 3. So that means the numerator degree is less than the denominator degree, which in this case means that is case 1. So case 1 says that means there's a horizontal asymptote at y equals 0. So if I were to graph this, you would see that the y values are approaching 0. So I just plugged it in my graph real quick. That should hit zoom 6 for a standard window. And you can see that the graph is getting closer and closer to these values of 0. If I hit trace, let's go to the right, you would see that the y values are getting closer and closer to 0, but aren't actually going to reach 0, even though it looks like it stops right there. The graph doesn't stop. It keeps going, following the asymptote, which we've talked about before. So looking at this last one, again, it's in standard form. So this is a degree 2 over degree 1. So this is the numerator degree is bigger than the denominator degree. So this is case 3. So that means the horizontal asymptote is none, and means we have a slant asymptote. So how do I figure out where that slant asymptote is? I actually use long division or synthetic division. So remember, we can use synthetic division if we're dividing by a linear binomial. Binomial means 2 terms. It's linear because it's to the first power. And so that means that, remember, the number that makes it 0 goes in the box. So x minus 3 equals 0, so x equals 3 goes here. Then the coefficients, 1, -4, and -5. Remember, if you're missing a 0 placeholder, add those in. The first number comes down. 1 times 3 is 3. Add these numbers together to get -1. -1 times 3 is -3, which gives me, add these together, -8. That's the remainder. So if this is degree 2, we want to put the x's back in. So this would be y equals x minus 1. And remember, the last number is remainder, so -8 over x minus 3. Now, when you are writing the slant asymptote, that remainder is really small. You don't actually have to write it. So the slant asymptote would be at y is equal to x minus 1. We don't have to write the denominator or the remainder because it's so small. So let's go ahead and take a look at this graph. So make sure, again, if you're looking at the graph, put parentheses around the numerator and denominator. So if I hit graph, again, we're not concerned with the vertical asymptotes or the holes, we're looking at the ends of the graph. So you can see the ends of the graph are going here and here. So if I go to my y equals, I'm going to plug in to my y equals that asymptote that we said. So the asymptote we said was x minus 1. And I'm going to make that a thicker line so you can see that the ends of your graph follow along the asymptote. So you can see it's following that asymptote. So that is our slant asymptote. So we can use our asymptotes to help us write out the end behavior. So that's the next thing we're going to do is write the end behavior. So the end behavior follows your asymptotes. So this would mean as x approaches either positive or negative infinity, your y values were approaching the horizontal asymptote of 3 because it follows along your asymptote. Here, as x approaches either positive or negative infinity in the long run, your y values are going to be approaching 2/3. We saw that when we looked at the graph. Here, as x approaches plus or minus infinity, your y values are approaching 0. Again, we saw that when we looked at the graph. Now here, the slant asymptote's different. So for this one, you're not approaching the same value as you approach plus or minus infinity. Let's go back to the graph. So as we go towards positive infinity, we're going towards positive infinity, and as we go towards negative infinity, we're going down to negative infinity on our graph. So look at this function. This is a polynomial function, yx minus 1. We talked about polynomials in the last unit. So this is odd, positive. It's an odd degree with a positive leading coefficient. So the left end went down, and the right end in the long run goes up. So we have to write this separately. As x approaches infinity, your y values go towards infinity. And as x approaches negative infinity, the y values approach negative infinity. So this is the end behavior. Now, technically, this wasn't part of the question. It was just asking us to find the horizontal or slant asymptotes, but you might have some questions that ask you to find the end behavior, so that's why I wanted to take a look at it. And that's it.